introduced quasi-probability decomposition method in a previous video. Now we explain the magic in it. As we mentioned, to mitigate measurement errors, we need B, the one recording measurement error information, and for state preparation errors, we need A. However, neither of them can be measured directly from a quantum device, even though we know there are two parts. What we can get is the Gram matrix, the combination of A and B. To calculate B, we need A, while to know A, we need B. It's like the chicken or eggs problem. So, what should we do? We guess. With G, we know the relationships between our elements in A and B. They are a set of quadratic equations. If we have sufficient equations, we could possibly solve that. However, we do not have enough information. It is an undercomplete problem. So finding A and B is solving an undercomplete problem. For such problems, we could have multiple solutions, and we don't know which one is closer to the true physical reality. Fortunately, we could choose bounds and constraints based on the knowledge we know. For example, both A and B are Pauli transfer matrices, so the elements should be between -1 and 1. We could add more bounds, but we have to be extremely careful with this, because adding bounds or constraints is also another way to manually add information. We should always question ourselves, is the artificial information right for a real quantum device? Is that the truth? Ultimately, we are just a human. We are not quantum devices. We don't know them well. We don't know if God plays dice. Another thing we could do for this undercomplete problem is adding measured information from the quantum device. That is, measuring more states in more measurement bases for Gram matrix. We don't need to worry about the validity of those information, but we do need to pay more quantum resources. A good news is that, at least, after we get A and B, we could check if the solutions are reasonable, even though they are not the exact truth. Two ways. First, we could reconstruct density matrix with only A, that is, with only state preparation errors, and construct another one with the whole span errors. Then we check the fidelity. That with only A should always have higher fidelity than that with whole span. This is simple, but another check is more important. That is, to mitigate the readout errors only. If B is acceptable, correcting readout errors with B should make corrected data better. It should never yield worse results than raw data. By the way, you might ask, why don't we try to get the complete information? We could, and that is essentially what get-set tomography do. Considering that there are fluctuations when you get data, you are likely to get unphysical results. So if you're desperate for the truth, you may need over-complete data. However, currently, quantum resource is still precious.